Thank you very much, and thank you for IBM for inviting me to give this tutorial. I want to talk about where design reliability is going to, and I want to make the case that safety is everything, and this is the most important topic right now in designing and manufacturing of semiconductor products. So if we look at what happened in the previous century, in the previous millennium, the computer age more or less started with ENIAC and evolved through the first stored program machine, the first mini computer, the first PC, well, it was Apple, and then the IBM PC itself, and the notebooks. And you could see a clear chain of development of the computer in this half century. Extending it to the current century, we can see the iPhone, we can see tons of drones erupting all over the place for multiple reasons, and everybody's expecting in the middle of the next decade to start seeing automatically driven cars. And my point is that there's a major break, a major disconnect in this history, which, as posted, seems very linear. So we have more and more computers. There are more and more. They have more and more memory. They're stronger, but there is a breaking point, and the breaking point becomes clearer if you look into the future. So where are we going in the future? We are going into things like cyborg organs and limbs. We're going into things like physical object computer games. We're going into things like danger sensing, computers playing, robots playing music, a robotic nanny. All of these applications. And these pose a dramatic change from what we have seen before. We are at a tipping point because the computers are fleeing their cages. All the years until more or less today, computers lived in a cage. They lived in a virtual world. Well, the worst thing that could happen to a computer would be a blue screen. Sure, if you have your money on it, you wouldn't want your money to be erased. And if you have other important data, you would want to protect it. But basically, a computer lived in its cage, in its own virtual world, and you interacted with it, and then you went off into the real world. The computers today, in this decade, are breaking out of that paradigm and are starting to interact in the real world. And this is most seen today in the automotive industry. And we'll come back to the automotive industry in this presentation because a lot of the things are happening in the automotive industry first. And think about it. Now, if you have an error in your software or in your hardware, you don't get a blue screen. You get a car collapse into another car. Sorry, blacked out for a second. We have a collision of two cars. We have someone dead. The importance of safety is no longer what's the probability of the money in the bank being erased. It's the probability of people dying. So the notion of first do no harm becomes dramatically more important now. It's no longer just some aspect that you want to include in your designs. Yeah, it's also safe. It is the critical thing. There are completely new threats. Whoever thought that if I'm designing an a semiconductor, or if I'm writing software, I can be held liable for a death. I can go before a court. I can go to jail because I miswrote my software. Who heard about going to jail because some software wasn't good enough? But if someone dies from it, it becomes a probability. And this, my belief is that this is a bigger change than even the previous one, which was the low power shift. So up to the approximately 2000, we only cared about performance. Then we suddenly cared about power performance. I'm saying that now we will need to care about safety, and oh yeah, also power performance. So the stakes have gone up dramatically. we need to rethink the way we're working. And what I want to talk about today is about this rethinking. How should we start thinking of our designs and our validation in the world where harm becomes very tangible? As I mentioned, I believe that the automotive industry is leading the way because, first of all, it's a perfect example of computers in the real world. These are computers. There are 150 microcontrollers in a car today. It is interacting in the real world with real dangers today, and they have a stepping stone philosophy, a stepping stone strategy of automated driving, moving, as you can see here in the picture, from no automation to driver assistance, partial automation, conditional automation, high automation, and full automation, where the first three have the human driver monitoring the driving environment, and these help him. They can beep. I have something in my car that beeps if I do something bad, like shift lanes without signaling and things like that. But in these three, the automated driving system monitors the driving environment. It starts with the adaptive cruise control, and it goes on to self-parking, self-driving in highways, all of these things, all the way up to the Google car that we've all seen that has no active driver. They're designing it with no driving wheel and no pedals. You are a passenger, you have no control. This domain of automotive has already started working on safety, obviously. There's a standard, it was published in 2011, and it is now being revised. The new revised version is expected around 2018. It's called ISO 26262. I will mention it a couple of times today in the discussion. And in 2012, we already had the first microprocessor certification to that standard, which was a free-scale semiconductor qualified by Exciter. And these are the first steps in this area. This is the first time that a semiconductor had to be validated at this level. Sure, aerospace always had special needs, and the military sometimes had special needs, but it was never a big market. This is the big market. These are the areas where the future integrated devices will go into. So we need to start thinking about all the aspects of safety. So I went and studied, what are the aspects. This foil is based on work from something called the Trustworthy Software Framework. There are other ways of organizing this, but we need to think about safety in a comprehensive manner. Again, we are validation people. We need to start seeing this as a major topic, as a major comprehensive approach. So there's safety, which is the ability to operate without causing harm to anyone or anything. There's also reliability, the ability to operate correctly. Because if you misdesign the decision whether the road is clear or not, you get the accident that was in the summer where a white sideways moving transport car was unidentified by the camera system, and we had a crash. You have to have availability. It has to operate always. It cannot be sometimes or when the conditions are favorable. It has to always be available. It has to withstand hazards posed by nature. It goes all the way from rain to radiation effects, to humidity, to noise, to dust. All of these things are no excuses. The whole approach here is zero excuses approach. And you have to have security, because beyond all the things that we just mentioned, there's always malice. The other aspects deal with nature or errors, but people sitting out there intentionally trying to break your system are a facet of life today, and the system has to be able to show that it is safe from them. So mapping this to what's happening in automotive, you can see that ISO 26262 is already addressing at least 3 of these aspects. It is talking about safety, it is talking about availability, and it's talking about resilience. There are 2 brother or sibling approaches that are trying to address the missing aspects. Selective, the safety of the intended function, is branching off nowadays from the 26262 effort and will probably become a separate document that needs to address reliability. Did I do my design upfront correctly? Whereas the current standard mostly looks at mishaps, assuming everything that was designed perfectly, how mishaps can deteriorate it. And there's also talk about a new ISO SAE standard about the security process. What do I need to do? What checklists do I need to make sure I've covered to protect my design from reasonable, probably, malice or accident? Extremely talented people will always be able to break things, but from a reasonable attack, how can I protect? So basically what I'm saying is that you have to think about all of these standards, all of these aspects, and that the automotive industry as a good example of existing activities in this area has already thought about most of them and is therefore a good place to start studying. So what does this mean for you? I'm saying that this is basically new to the computing smartphone industry. Again, perhaps not to the people who did aerospace, but most of the companies, most of the people doing computers, notebooks, phones, games, all of this is new to them. We have to reinvent the design methodology, and again, the best example I can show is how we had to start integrating power everywhere. You can't put power on top at the end, like you can't put quality at the end. Safety is going to be a new revolution. It's of course based on system engineering. So we all, to some level of another, are working in the system engineering aspect. So we have to add a system engineering with safety mindset. There is the standard, which is leading the way, which is a great first step into the world of safety. But don't worry, it's not the only standard. I've picked a few of the other standards which are relevant for safety, and the list, it is just a sampling of the relevant standards. There are many, depending on what domain you are in, what's the use, what kind of design you're doing, what you're manufacturing like, and so on.
Is there room for questions?
Yes, good point. I tend to talk, but I love questions. So if you have a question, interrupt me like this gentleman, and I'll be happy to talk. Yes?
So you said that you get certification according to this standard. This is the same kind of certification you get today for ISO, which is you following a certain kind of procedures, and if you did that, then you are secure, available, reliable, etc., etc. Or you actually do more than that?
I think the best answer would be yes. On the one hand, the standards are by nature mostly process-oriented. They say, did you check this? Did you document this? The ISO 26262 standard most of the time says, show or prove or demonstrate or write down the reasoning and so on. Part of the process would be to convince someone, for example, the person who's auditing the process, the person who's supposed to, at the end, to sign off that it is safe. Did you convince, did you put a good argument that this is so? For example, you have to show, and we'll talk about it later, that the design is acceptably safe. The probability of a problem is below the threshold that is set in the standard. You have to make the argument, you have to bring the data and prove it. Now, the best part about these standards is that they are not enforced. Nobody forces you to follow 26262. But if there is a trial, and trust me, there will be a trial, and you are held on liability because someone dies, because in cars, people die. Today, over 1.25 million people die every year from automobile accidents. So even if we get it 100 times better, it will still be 12,000 people dead, and each one of them a liability suit. So in the trial, you will be asked by the lawyers and by the judge, did you use good working methodologies? Did you use the best known methods? Are you following the standard procedures? And then you bring your papers and you show the arguments. So the arguments that you prove to your auditor are just a rehearsal. You will re-show them later, after the fact, in a trial. So it really behooves you to be very, very careful in the way you do it. Bottom line, the validation of your work is, can you convince a reasonable reader that this is a good path that you've chosen? Does that answer the question? Any other questions? Thank you. The bottom line here is that you need to think about safety, which is the point of my presentation today. So, if you want to start thinking about safety, what do you need to do? Basically, you need to start balancing cost versus safety, because in many areas, you can have perfect safety at unacceptable costs, and we'll show some examples later. And you need to start navigating this forest of standards and understanding what applies to you and how you need to do it. But basically, it starts with system engineering and a structured methodology that works on safety, and so we can get started. All this was the exposition. All this was trying to explain to you why this lecture is interesting for you, why it's relevant for you, and I hope that I have convinced you that safety is something you really want to start looking at. So what can the automotive industry teach us? So this is a bad first foil. It tries to quickly say what the US government is looking for. The US government, through its National Highway system, is requesting that every person who plans to have an automatic or assisted automatic car will declare to the government what they plan to do in various topics. So I didn't find a good way to make this interesting to read, but basically what the US government is asking manufacturers to show is that they have fail-safe, that even if something fails, they have a way to control it and handle it and not just randomly crash. Then, are you following industry standards? Again, this is the best known method, so can you show that you are following the standards? Are you doing hazard analysis and safety risk assessment? And this will be part of what I'll be talking about today. What are hazard analysis? What are risk analysis? And what does that mean for you? Do you provide redundancies and safety strategies for system malfunction? First, you need to think about the fact that the system will malfunction. That is a fact. But what are you going to do about it is what you need to think. Are you just building in redundancies that if one copy fails, the rest will pick it up? Do you have other safety strategies? What are you going to do when something fails? Are you making sure that the software is properly developed? Are you monitoring the best known situation in the world of what's happening in AI, in machine learning, and so on? And just as an example, machine learning today is one of the most unsafe software practices. Because think about it. How do you validate a machine learning system? Let's start with a simple machine learning system. A one that you pre-program in the factory and then you deliver as is to everybody who buys your system. How do you validate it? Do you run tests on it? We ran tests on it. That's how it learned. Do you compare it to other options? Sure, we do that. But that is basically simulation-based validation, nothing more. How do I validate it beyond that? I don't know. Machine learning that keeps learning after you sell it is even worse. You don't really know what will happen. What are you validating? Are you going to validate the algorithms that teach the machine, or are you going to validate what the machine will do once it's learned? So just a way of thinking, this is why they're saying, make sure you are on top of the latest research in these areas, because maybe someone will find an answer. Are you making sure you're linking your design decisions to the risks? That you make sure that you understand whenever you make a design decision, what is impacted by that. And I'll give an example in a couple of slides about what happens when that goes wrong. Are you testing and validating everything, both as subsystems and the whole system. And again, as validation people, you know about this, and you're fully documenting the whole system. This is where you can find the whole thing. Page 20 talks about safety. They have many other issues that they are concerned about. So what is 26262 standard? Basically, it starts with defining functional safety as the absence of unreasonable risk due to hazards caused by malfunctioning behavior of electrical or electronic systems. And I emphasize here unreasonable risk, because there is no way to make something risk-free. No way to make it risk-free. The best we can hope for is to have the risk be reasonable, acceptable, a risk that you are willing to take. Risks, for example, are usually measured in fit, failure in time. And the usual metric of fit, of 1 fit, is 1 failure in 10 to the power of 9 seconds, which is approximately once every 100,000 years, which means that if a car, say an average car lasts for 10 years, that means 1 in every 10,000 cars will have a fault, no more. That is 1 fit. If you have 5 feet, then 5 in 10,000 cars. The idea is that you have to set a reasonable level and say, yeah, I'm willing to buy a car, even though 1 in every 10,000 of it will have 1 fault in its whole lifetime, the rest will have 0. This is acceptable risk. Acceptable risk is not high, but it's, again, not 0. And risks come from systemic failures and from random hardware failures. These are the 2 big sources of problems. One, as typically people from validation know the first one very well, less so the second one. So systemic failures are misdesigns, places where we designed something badly or we didn't think about some aspect of it. These are protected by good design practices, good validation practices, basically the way we did validation up to today. The new part is random hardware failures. It says a perfectly designed part, some grain of salt, some humidity, some radiation from outer space came and did something bad to it. What happens now? And this is the area where we need to start thinking anew about what we're doing. And the whole 26262 is process-based, as you asked before, similar to most other standards. You cannot specify you have to do X, Y, Z. It is specifying up to a point, but it says show an argument that prove that you have done this or that. So, in a nutshell, the ISO 262 is a process, and the goal is to lower risks until they become lower than the preset threshold. This is like what you need to remember about the 26262. So what's the process? Here's the process in a nutshell. This is taken from the actual document of the process itself. And basically what it says is you do the hazard analysis, you conceptualize the functional safety, and then at each level you make sure that it is done correctly, validate the safety, integrate the whole thing, and move to production and servicing. Surprise! Yeah. So again, process standards tend to be very similar. It's the details that differentiate. If we go into slightly more detail, the new parts are that you need to specify hardware safety requirements, you need to evaluate the metrics, and you need to evaluate how many goals are violated so that you know what to do and if you need to fix things. So let's go into the actual details. What do I need to do? What is this process that you're talking about? What process do I need to follow in order to be safe? And the process says, first, identify the hazards and assess the risk for each hazard. So what can go wrong? This line can be torn, this part can be broken, or if you're looking at the semiconductor part, this flop can be can get a bad value, or this line can be disconnected. Some of it is similar to manufacturing testing, like hard errors, like stacked faults. Some are the soft errors that some of people I know are working on, where again radiation can flip a value, and then the part continues working as usual, but with the wrong value. You need to think about all the hazards, and for each one, decide what might go wrong about it. Then you need to classify them into buckets. There are three things we want to understand. What is the severity of this risk? If it happens, what is the worst thing that can happen? Are we talking a death here, or are we talking about the car will go slower and it will take you more time to get to where you want to go? So how bad is the injury? I want to understand what is the exposure, which is more or less the same as what's the probability of this happening. Is this something that can happen every day, or is it something that is very, very seldom? Yes?
We're talking about the car industry. And in fact, the problem was already solved in all those race cars. They hit the wall in 300 kilometers per hour, and the driver comes out.
Yeah.
So this was solved, but the problem is that the other problem was solved as well. Human lives are not so valuable. We don't care.
Yeah.
Right? If you die, no big deal.
Yeah.
We care about the race driver, but we don't care about the regular person. So to have to deliver a race car to every individual will cost him $500 million. Nobody wants to do it.
Exactly.
And this is not in the process, the cost.
It will be in a minute, but I think in a nutshell, what's your name? Itzhak's point is exactly the point of the process, and that is affordable safety. Basically, what we need to understand first is what are the safety requirements, and then can we make them affordable? Can we do them in a way that will not cost me $500,000, $500 million, I know they said $500 million, but $500,000 for a car. I will not buy a $500,000 car, and I still want it to be safe. So that will become into the engineering of trade-offs between safety and cost. But first, I wanted to make sure we understand what is the safety, because everybody understands cost. So the last thing, which is maybe new to some people, is the controllability. There are some problems that a good driver can overcome pretty easily, or at least detect. So if this particular hazard comes into play, then the car will start emitting black smoke and making a very loud noise. Probably the driver will notice something amiss and will stop the car. So this is a high probability that the driver will notice and will control it. On the other hand, maybe the brakes have quietly disappeared. The first time the driver will know is when he tries to hit the brake pedal and nothing happens. That is not very well detected. So if the driver can detect it in time, or can control it in time pretty easily, then it is low, it is controllable. It's less of a problem. The less the driver can override it, the worse it is in terms of the overall classification. So given the severity, the exposure, and the controllability, I set an acceptable risk level. So for example, as I mentioned before, if it has high severity, high exposure, high controllability, then I would want something in the order of 1 into the 10 to minus 9 seconds, something that should almost never happen. If it's something that is less severe, I don't care if it is a higher risk. Safety mechanisms, after you have decided what are the biggest things, the most important thing to control, start thinking how you control them, to either prevent the risk or at least detect and react to it. And that is where the engineering comes into play. You need to figure out what to do for each risk, lowering it, again, never making it go away, lowering it to an acceptable level. And finally, of course, you need to analyze what you've got and say, okay, given that these are the risks, these are the safety mechanisms, these are the probabilities, what's the bottom line? What is the probability of something bad happening given everything that I've done before? This is the basic flow of how you protect yourself and making sure that your design is safe. So let's go slightly more detail into each one of these. The identifying the hazard starts with a malfunction. It's always about a malfunction. So if something goes wrong and I'm in a bad weather, or I have a distracted driver who is not really focused on what's happening, or I'm in a crowded town with a lot of traffic jams, or I'm some other situation. What is the situation that will make it worse? In what situation would it be the most hazardous, this particular malfunction? So you think about the malfunction and you enhance it to become as hazard by taking into account what would be the worst case scenario in terms of both the probability of it and the environment around it. So maybe if you are in this situation, it's very dangerous, but you don't expect it, but it's not an all-terrain car, so you don't really care about this situation. This situation where someone is driving at 240, by the way, and not completely legal, at 240 kilometers per hour, if he's driving this fast, and there are many people who do, then it's a different hazard, it's slightly less, but also important. So you need to think about all these combinations and make sure that you document them carefully. And again, remember the trial. If something happened and it wasn't even in your tables, some hazard happened and killed someone, and they say, where's your documents? Where did you check all the hazards? Is it in there? And you say, no, I didn't think about it. Not so good. So you need to identify and categorize hazards triggered by malfunctions. And here's a cautionary tale, okay? So this is a real-life situation where General Motors had an ignition switch that occasionally turned itself off without any visible reason. So what happened? Okay, they didn't think about this potential, but let's think about it now. What can happen if an ignition switch turns off when you're, anytime, when you're driving, doing whatever, all of a sudden your ignition switch turns off? Any ideas what can go wrong? What can happen?
You lose brakes and control power.
You lose power steering, you lose brakes, you lose control. Absolutely. So you can have a car stalling on the highway. You can have no engine. You have very limited driver control. What else? What else can go wrong in such a situation? Okay, thinking about hazards. Well, in an unrelated situation, an unrelated story, General Motors was concerned about their airbags exploding. Now, I don't know if many people here saw an airbag exploding. It's a big explosion. And they were concerned that people will get hurt by airbags exploding when not really needed. So they have this wheezy safety idea. If the car is turned off, who needs airbags? So they, in an unrelated story, decided to have no airbags when the switch is off. Now you have all of these things that we mentioned before, plus no airbags. Okay? You need to think about all the consequences of design decisions, and all the hazards that can happen, given everything else. And this was 100 or 200 deaths, a major trial, a huge recall, and a very big black eye for General Motors. Something looking like, you can Google it up, it's a real story, and this is the car that started the trial that found all of these problems. After I've identified the hazard, I need to classify them. So I don't really expect you to learn all this, just to give you the sense of it. Each one of these criteria has levels. So exposure can be something which is incredible, like what happens if an aeroplane will land on the highway next to me? Okay, it happened, we all saw the movie, not very frequently. Or it can be very low probability, low, medium, or high probability, which is over 10%. If it's a probability of over 10%, we call it high. This is something that really you want to protect against. Again, the severity. If it's only material damage, yeah, let's ignore it for now. if it's all the way up to life-threatening, it's something I want to really worry about. And controllability, something which is controllable in general, either by the driver doing something to compensate, or at least by identifying and then stopping, then we can ignore. But things that are difficult to control or uncontrollable are bad. And here's the table that says, given all of these answers, you can go all the way from the green, which says, I don't worry about it, it's just general quality problem, all the way to red, which says, this is something I really, really want to protect against. This is something you cannot ignore. It has to be very strict and very infrequent to be called safe. Next, I want to specify the safety mechanisms that mitigate the unacceptable risk. And that means that for each, I do all of this analysis. I go into safety goals. What are the safety goals? I set goals to myself. For example, the car will never brake unless the driver initiated the brake sequence. Or the car will never brake unless the system really detected correctly a situation that braking is needed. So this can be a goal. You derive from it in the usual way specific safety requirements. You specify how important they are. You specify them into the specific products and so on. So this is a classical derivation tree going all the way from abstract requirements all the way to the detailed requirements. And you need to control all of these things. You need to control the internal failures of the hardware, but also failures external to the hardware. Maybe some of your inputs are corrupted. What will happen then? You need to comply with safety requirements of other elements. They depend on you. They require that you behave in a certain way. How are you ensuring that? How are you detecting the signals for failures? How are you meeting the target values I mentioned before for the random hardware failures? How do you avoid specific behaviors? For example, a safety goal here can be a particular sensor shall not produce an unstable output signal. It has to be within certain variations of the voltage level, for example. And last but definitely not least, are you implementing the intended functionality? Not only are you protected from random problems, but are you doing the work that you are supposed to be doing? And finally, you need to start thinking, okay, so I identified all the hazards. I specified all the needed goals. I put in all the safety mechanisms that I could think of. Now, bottom line, what do I have? Is it safe enough or not? How can I tell? So basically, risk is derived, as I mentioned before, from two big areas. One is systemic and one is random. If we are thinking about a systemic risk, you're going back to what we are all familiar with, which is how do I make sure that my hardware and software are bug-free, and it's always done by good design and by good validation and by good management to ensure that the product is relatively bug-free. How do I handle random hardware failures? Less obvious. We start by partitioning them into the two big groups of random failures. Transients, the ones that come and go, and after they are gone, but while they are there, they might do something bad. And permanents, which are like a wire breaking, a transistor blowing out, something which is a damage and it's damage for good. By the way, again, I'm not stopping for questions, but feel free to ask questions. Itzhak seems to have left, but other people are also invited to ask. So, as I mentioned, we have transient, bit flips, and permanent faults. Transients come from outer space, typically, from the radiation that is found in outer space. As it percolates into our atmosphere and hits a part, it can sometimes cause a bit flip, depending on many considerations. But there's a certain rate at which bits are flipped in our design because of external radiation. And hard errors are, as you can see here, some of them come from the sun, and some of them come from outside the solar system. So both types are relevant in this case. And hardware failures are really, disconnect, breakages, a transistor can be blown, various other hardware breakages. So again, I've mentioned all of this, and it's in the foils, you can see it later. And just to make sure people don't happen to think that this is theoretical. Another real life story, in this case coming from Toyota, when they had a recall because of an accident that couldn't be identified as to the source. And the people covering the story are saying that as little as a single bit flip can cause a driver to lose control of the engine speed in real cars. Memory corruption as little as one bit flip can cause a task to die. This can happen by hardware single event upsets, i.e. bit flip. So in this particular case, which is a real case in a real court, with a real recall of cars, they believe that the root cause was that they were not protected well enough against these transient problems, so that a single bit being flipped and then everything else continuing as usual, but it had a 0 instead of a 1 or vice versa, it caused a driver all the way from a single bit was connected all the way up to a driver losing control of the car. Again, a small problem that we typically say, well, okay, we'll get a blue screen, can get someone killed. This is the new world where we are. Yeah, go ahead.
I mean, how can you do that after the fact? I mean,
Okay, wonderful. You can't.
no recall, right?
You can't. What in this case, what they did is they say, can. And this is a quote from an expert witness in this trial. He said, we've demonstrated how this can cause the driver to lose control due to software malfunction. He did not say that this particular accident was due to it. There's no way you can know that. But he said that he can show on their model that they are not safe enough from soft errors. And really the best way you can prove it is by showing that all other explanations don't hold. So if you have a problem, that you can see the problem, but you can't see a reason, typically you would ascertain it to this. So again, on the one hand, yeah, you can't prove it. This is a real case in a real evidence, and it was enough to get them fined a couple of $1 million, and the US government to force them to do a recall. So, you can't prove it in theory. In practice, it's just a question of convincing 12 good men that it is a problem, and you're done. So, yeah, we typically cannot see this in the physical evidence after the fact. Yeah, another question? Again, very technical. I don't know how much details you want to dive into. This talks about classification of faults. And I'm talking about faults as individuals, but in actual fact, the fault itself is not atomic. We often partition a single fault into probabilities. What is the probability that this fault will happen, will cause this and cause that? So the allocation is not integer faults, it's fractional faults with probabilities. But let's look at complete faults. So basically, I take a fault. Something broke. For example, I take all the flop bits of my chip, and for each one I ask, if this bit were to flip, no other change, but this bit has flipped, what would happen? So, first question, can it do any harm? If this bit flips, can it do any harm? Sometimes, some structures I can know up front. For example, it's part of the entertainment system. It cannot connect it to anything real. I can say, no, it doesn't, no, never. It can never impact anything important, and this is a safe fault. Sometimes the fault by itself can cause a problem. If this is the line going to the brakes, and a bit being transferred on this line says hit the brakes, then a fault here immediately hits the brakes, immediately causes a problem. Then I want to say, is there a safety mechanism? Is there some way of protecting? Is there redundancy? Is there some checks? I don't know, something. If there is, okay, does it detect, does the safety mechanism detect it? If not, if there is a driver, can the driver intervene here? If not, it is a residual fault. These are like the baddest of the faults, the ones that we didn't catch. If there's no safety mechanism, it's a single point fault. These two are very similar. This is a fault that has no safety mechanism, and this is a fault that has a safety mechanism, which is no good for it. So these two are bad. If it's a detected fault, a perceived fault, then okay, I can live with it. It's a fault, but we have control over it. And sometimes a fault doesn't happen by itself, but it doesn't impact anything by itself. But if you have two faults together, then it can be a problem. For example, if I have a system and a tracker system. So if the system has a problem, then the tracker will catch it. If the tracker has a problem, then the system will be different from it, and overall, we know how to deal with mismatches. If both of them have a problem, then I might not be able to detect anything, and I might get a bad result. So sometimes a fault can cause what is a latent fault. That is, it has happened, it has some lurking problem, it leaves something in the memory that is lurking there, and if ever a second problem will occur, the accumulation of both of them will kill someone. So we allocate all of these faults, all of these buckets, and now the question is, well, what is a good result and what is a bad result? So there are two metrics, the single point fault metric and the latent fault metric, which is completely illegible at this level, so I try to put it in graphs and say, the first is, I take how many bad faults are out of the overall fault. So I'm looking at the ratio between the faults that are critical of the overall faults in the system. This I want to have, like for the highest level, I want to be no more than 1 in 1,000. So I would like that no more than 1 in 1,000 will be bad faults from all the faults in the system. Yeah.
So the more entertainment systems I add to my car, the safer you call it.
True. True. There are pitfalls in this formulae, and some people are even silly enough to try and do that in real engineering. They say, okay, I will add, for example, memory, which is ECC controlled and therefore has a zero probability of failure, and then I will dilute the problems. Well, for that, there are other metrics, complementary metrics, that will catch it. For example, going back to the fit, what is the probability of a problem happening? So yes, there are ways to get around this, and some people are, as I said, silly enough to try and use them, but the real metric, from my perspective, is the fit rate. And there you cannot cheat, because it doesn't matter how many infotainment parts you add, you do not really dilute the failure in time aspect. So, good point, and you should not do that, but if you are doing things in good faith, this is a good metric for yourself to see how well are you connected, how well are you safe, and similarly, I want to see how many latent faults of all the non-critical faults. How many of the faults that don't kill you are lying there lurking and will catch you later. And again, the goal is to be under 10%, and yes, you can always dilute things. So, what do? For every safety goal, I say, sum the probabilities of all the faults that violated, and here is the metric that I mentioned before, the fit rate, where you cannot dilute. What is the probability of all the faults that violated? Take all the ones that are still out there and I didn't catch, And for each one, you compute the probability that it will happen. For example, for soft errors, we know the radiation rate for New York City at sea level, and you can correct for other places, but the difference between sea level and 1 mile high is not that big, so you can average it out. You know the probability for a bit flipping, and then you decide how many bits are critical and multiply the probability that they will be critical by the probability that they will be hit. You can get a reasonable metric of the probability, and you get a target of 10 to the minus 8 per hour for ACIL D and 10 to the minus 7 per hour for ACIL C and B. D, if you remember before, we saw it in the table, is the critical ones. B and C are less critical. Is it under the target? Then it is acceptable safety level. It's not safe. It still has a positive probability of problem, but it is safe enough. I can live with it. And of course, if it is above it, it's unacceptable safety level. It must be fixed. You cannot manufacture and give people products that are in this red zone. Questions? So what do I do about this risk? I keep saying safety mechanisms and so on. How do I mitigate the risk? Basically, there are 4 systems that you can deploy. The first is well known, and I will not go into it at all, and that's error detection and correction schemas. For memories, and today even for buses, I add redundancy to the memory, and I apply some system that can detect X amount of bits and correct Y smaller or equal to X number of X, typically smaller than X, depending on how much I want to pay. So the more errors I want to be able to detect, the more redundancy I need to add, the more cost. But all of this is well known because memories are known for a while now to be sensitive, and therefore they have solutions. The rest of the design, the random logic, is not so happy, it doesn't have a good solution. Then I go into redundancy. Now redundancy, I will show you in a minute, is a wonderful type of solution of the type that Yitzhak mentioned before. It can be very good and very expensive. For hard errors, I deploy software or hardware tests similar to the concept of manufacturability, or manufacturing tests. That when you manufacture and you test basically for hard errors. The whole area of manufacturing tests can be reasonably adapted to the area of hard errors. And for soft errors, there's a notion called flop hardening, where you can protect specific flops or all the flops from the problem. So let's study the bottom 3. As I said, the ECCs are pretty known. I didn't want to spend any time with them. So protection by redundancy. I can have 2x, 3x, and even 9x redundancies, depending on how paranoid I want to be. So the 2x is often called lockstep. Basically what you have 2 copies of the same design and a comparator. The comparator can detect that they disagree. As long as they agree, I take the consensus answer as the real answer. Remember, I don't want to go to perfectly safe. I want to go to reasonably safe. This solution gets me the square of the probability of each one of them failing. So if one of them fails every 2 to the minus 5, this combination will be 10 to the minus 10. So I immediately go in way below, typically I would go way below any reasonable probability limit, because the probability of them breaking in the same flop, in both copies, getting the same problem and getting the same wrong answer is the square of the probabilities, and typically I can ignore it.
At the same time?
At the same time, because these are all transient. Well, okay, I stand corrected. When talking about transient, it's at the same time. If you're talking about hard errors, then yes, at any time at all. But if it's not at the same time, you would get an error indication and that will give you an indication to replace the whole subsystem. And if you have an error indication of replace the whole subsystem and then it disappears, you really, really want to be worried now. So all of these can be controlled externally. So bottom line, yes, at the same time. What's the problem with this option of lockstep? Anybody?
So no correction to the error.
No correction to the error. So what do I do? Okay, the error bit goes high. Now what do I do? It goes low in this case. And what do I do? I have to know what can be done. So if this system is an optional system and it can be disconnected at will with no bad consequences, wonderful. Then this is good. And if the bit goes up, I disconnect the subsystem and I'm fine. If it's a critical system, I go into the three-way comparison and I get the gate majority that again tells me that what to do. So as long as I have a majority and as long as no two get the same error at the same time, I'm not only safe from problems, and not only can I detect the problem, I can also decide what to do about it. If this is a single bit, then I just need to know that I corrected something to be worried. If it's a multiple bit, then I could have no consensus at all. If each one of these gives me a bus of 8 bits, then one can say one number, the second number, and the third number, and then I still have to figure out what to do. Again, if it's important enough, I can do this single bit and spend the money accordingly. 9x is something that the aerospace industry likes to do. They give the same design spec to 3 different companies. They get 3 different designs. They take 3 copies from each design. Each design votes internally in case of a hardware problem, of a transient problem, and all 3 designs take another vote in case of a design problem. So if someone had a bug in their design, it will be decided in the second voting. So 9x protects you in case of the design problems, at the trivial cost of spending 3 times as much for design, and then 9 times as much for copies. Obviously, this costs
say 9 or more.
9 or more. Yeah.
You have to integrate.
Yes, of course. Yeah, I'm rounding off, obviously. So this costs you about 2x. This costs you about 3x. This costs you about 9, 10, 12x, whatever. Expensive, as I said before. Now, this is the reference safety, because this is taken to be completely safe. It's not completely safe, but it's so small that it's almost completely safe. This is the ideal. Now, I want this level of safety with a 1x cost, not a 2x, definitely not a 9x. And this is the challenge that the design and the EDA companies need to face to understand affordable cost, safety. Alternately, if you're thinking about hard errors, you need to test. So basically, you run a test, a software or hardware test, intermittently every so often, and you need to decide how often, depending on how long you can go with a broken system. Typically, you would go like 1 millisecond. So every millisecond, you check your system, and that means that the worst case, you'll be 1 millisecond running with a bad part, and probably that's okay, depending on the specifics. You compare it to the golden result. If it fails, you enter and maintain a safe state, or you do something else that you want to do in case of a problem. The probability of error detection depends on the time to detection and the probability of detecting a fault. And the probability of detecting a fault is critical here, because unlike theory, in practice, a test does not cover all the possible hardware failures. It covers some, maybe many. We know in manufacturing tests, we use non-functional tests, structural tests, that get you very high, 96, 97, 98, theoretically even 100. In practice, you don't get 100%, and structural tests require rebooting the part before and after. Sometimes you can't afford this reboot. You go to functional tests. Functional tests has limited coverage. You don't get 100%, so you need to take account of how many faults does your test miss, and then for that you need a measurement of the test cost. The third option I mentioned is to do selective hardening for soft errors. Selective hardening works like this. Basically, the mechanism of a soft error starts with an external radiation that hits the part and throws some electrons and some holes around. So it basically looks like noise jitter. It looks like noise on all the system. If your flops are small enough, this jitter will overwhelm their capacitors and will flip them. If your flops are heavy and have a lot of capacitance, this noise will not hamper them. If you want to go to the extreme, you can do a three-way TMR for each flop separately. Actually, if you just do these things, it will cost you more than a regular part, but less than having three parts separately. So hardening your flops, let's start with hardening all your flops, can cost you, I don't know, a 1.5x of your chip, because flops are not that big a part from the overall chip area. So if it's like 10% of your chip is flops, then you can go to 1.3, 1.5x area. Not so good, but better than 3x for the three-way redundancy. The ideal would be to figure out which flops I want to harden, which flops are important and which flops are not, and then harden specifically the ones that will give me the biggest improvement in safety. And this is how you do that. You start with a list of all your flops and the sensitivity. Sensitivity says, given that a bit in this flop is flipped, what is the probability of something bad happening? It is not always 100%. Sometimes it's 100%, sometimes it's 0, and sometimes it's in the middle. If I know this, and this is a huge if, I know the probability that a bit flip here will cause something bad. Then I can do the next step and decide for each flop separately what kind of flop implementation I want to use. What library do I use? Do I use a standard library? Do I use a big capacitance library? Do I use a TMR library? What kind of library do I want to use for this particular flop? If I know that, I can go ahead and figure out how much does this cost me, because it's extra area for some of these. How much power am I dissipating now more, because bigger capacitors means more RC power to be dissipated every time I flip a flop. And what is the fit rate for this particular flop that I've chosen. I multiply the per flop probability by the probability of this particular flop to be critical, and I get the derated fit contribution. Now I can do classical engineering and do trade-off. I have the cost in area, the cost in power, and the fit. And I can play around with them by changing the flop type decision until I have the perfect balance between safety, power, and area. And all this depends on sensitivity results. So what we have seen is that for soft errors, what you really need is sensitivity. Similarly, for hard errors, what you really need is to know the coverage. How many tests do they cover? These are the two problems that we need to have good support, methodological support, and tool support, EDA support, to give me this information. With this information, I can get very low cost, very good safety balances. Without it, I have to do some brute force approaches. So, the overall flow that I'm talking about, I separate memory from logic. And again, the question is, how do I protect my design? Okay, if it's logic, if it's memory, just pick the right ECC and you're good to go. If it's logic, Are you okay with redundancy? Are you sensitive to cost? If cost is not a factor, wonderful. Pick the right redundancy. It's okay to implement, but you said you don't care about cost. This is going to be expensive. If it's too expensive, then let's separate for a minute soft and hard. You usually need both, but for the sake of discussion, let's talk about separately, soft and hard. If you need to talk about soft, and soft, I will not go into the details, you only need to care about registers, and then I go to see, is full hardening okay? If full hardening is okay, and basically this is a cost issue again, it will cost you more, but it will be easier to do. If you're okay with full hardening, just harden all the flops, it's okay to implement, but it's expensive. Not as expensive as this one, but still it's expensive. If it is too expensive for you, you need selective hardening. Similarly, for hard errors, you focus on all the nodes. Are you okay with a disruptive test? Again, disruptive because whenever you run it, you have to reboot the machine before and after. Sometimes that's okay. The machine isn't working all the time. You can take it offline, check it, bring it back online. Remember, once every millisecond. Sometimes the machine you're talking about cannot be taken offline. It depends on the details. So, depending on your situation. If disruptive test is okay, you can go to the DFT people in your design and ask them for the best system they have with the right parameters and runtime and cost and so on and memory. But this becomes, if disruptive test is okay, this becomes a manufacturing test problem, pretty much solved in the manufacturing world. You can negotiate with the DFT team and get the right answer. It's okay to implement, but it's disruptive. Remember, you said it's okay to take the part offline every millisecond. If it's not okay, then you need to create a functional test. And if you're doing a functional test, you need to understand the coverage metric for it. So this is the flow, and it leaves two questions. These two questions unanswered. How do I do that? How do I get this information to enable the system? Top-down view, I wanted to make a safe system. I understand I have to be good design, good validation for the systemic, and I need to do this flow for the random hardware errors. And in many cases, I need one of these two yellow bullets, yellow areas here that need to be solved so that I have a safe system. Questions? Anybody have an idea how this is related to the presentation? It's not. It's just a cute cat doing what cats are typically doing, which is being cute, and I just put it here to break the monotony of me talking all the time. Hi, cat. So, basically, the simulation-based approach, and simulation includes emulation, and I will not go today into the details why simulation is the only mechanism. We can go into more details offline, but basically, right now, although we have some people here from the formal world who are working on formal solutions, right now, the simulation solution is the main solution, and you need to do, basically using simulation, either selective hardening or coverage metric. Let's talk about selective hardening for a minute, and the key question is how accurate do you want it? So you can say, I don't need it very accurate. You can use expert opinion to select flops to harden. In the 2011 version of the standard, this is supposed to be an acceptable way of measuring things, that if an expert can look at the design and figure it out, and he looks at it and he says, I think it is 12%. Because I have a lot of experience, I'm old and wise, it's 12%, you can use 12%. In the new version, I'm in the committee that redrafts the new version, I push them to put in and explain why it is a good idea to have an expert instead of measuring, and can the expert please explain why this is the number and do some kind of proof and so on. This is very shaky. It's guessing the impact, there's no way to check it. You know, people try to do it. I wouldn't try to explain this in court. If accurate is sort of important, then you do some simulations you do some analysis, you do things like saying, oh, I have a bus of 64-bit bus. I'm assuming all the bits are the same, and I can just do one simulation and the rest will be the same. And other tricks, or again, the expert chooses nodes. The expert knows you can do a little simulation, and then you need to guard band the results. So if you are showing that you are 95% safe, you need to downgrade it to 90 or 85 to protect yourself from the unknown. Or you can do a full simulation, do exhaustive simulation, simulate all the flops, all the faults, all the possibilities, and remember this is time dependent. So the fault can be on flop 1 in time 100, time 101, time 102, all the times, all the flops, all the workload, and try to get an exhaustive. This will get you accurate results, but someone says here, time to market. How long will it take me? It will take you a long time or a short time, depending on how fast your fault simulator is. And we'll talk about fast fault simulators in a couple of slides. So similarly, for hardware coverage metric, how accurate do you want it? You can do some partial simulation, do some statistical coverage, guessing, guard banding, and so on. Or you can do exhaustive, identify. If you do exhaustive, not only can you get accurate results, but you can, in various techniques, get indications of how to improve. What are the critical nodes that you need to expose externally so that you can do better simulations? It has some path of improving coverage, which is always bad. Coverage of functional tests is always bad. And all you need is something that can run a simulation of 100 million flops design, 200 errors per flop, which means 200 million simulations in a week or two. That's what you want. And up to recently, this was not available in the market. Fault simulations obviously talk about simulating the good machine versus the faulty machine, given some fault details, and comparing them. And for soft error, you want to say, did the fault impact the safety goal? For hard error, was the fault detected? But essentially, it's the same idea. You simulate a good machine, you simulate a bad machine, you compare the outputs, and you decide if this means good or this means bad. For hard errors, I can decide which flop flips and when. For hard errors, which node breaks and how, what kind of breakage it is. This is the basic flow of using fault simulations. And all you need to do is repeat it for all relevant faults, assuming you know all the relevant faults, depending on your model, depending on your design. Yes, question?
So can you expand a little bit what does the simulator include? Does it include all the physical parameters of the environment? Heat, acceleration, speed, etc.?
No. What the simulation does is assumes that everything that you mentioned is encompassed here. So that all the external phenomena, eventually what they cause is a fault. I take it from the fault onward. So you're asking what caused this fault? Maybe it's the temperature, maybe it's a grain of dust, maybe it's external cosmic radiation. Once I have that, I have a fault that is visible in an RTL or a gate level simulator.
So it's not what I was asking. I was thinking that a fault would exhibit itself differently depending on the physical parameters, depending on what the machine needs to do right now.
True, but obviously the real world impacts my design in various ways. We are trying to model these things into software models that are usable. So what everybody is doing is assuming that the proper model for everything, all the phenomena that you have mentioned, is at the end of the day either one bit flipped or one line broke in some specific way. And everything that you are asking about the physical translated into this fault model. So the fault model that we are using for soft errors is a bit flip at some point in time that can be later overwritten like any other value. And for hard errors, the most common model is Stacked, but there are a few related failure models for hard errors that can also be understood. There is some research now to identify if for soft errors 1 bit flip is enough, or maybe we need to do 2 bit flips of adjacent nodes, because the phenomena of an external radiation can sometimes throw enough electrons and holes around to hit 2 very close together, in close proximity, 2 flops and change them both. So the question you're asking relates to fault models. I'm saying this is the fault model that we are using, and the partition line is one study says from physics to fault models. This talks about from fault models to danger or lack of danger in the overall system. Did I answer your question? Thank you. So, if you know all the faults, you just repeat for all the faults, and again, it's a question of how fast can you do it. So again, I'm in the EDA industry, and for us, this is what it means to have automatic safety. You need to manage specification and implementation. The whole process of specifying and interconnecting and so on is a management. It's similar to other system engineering activities, but it has to be done. It has to be monitored and audited. You need to select and apply the right safety goals, taking into account the design components. And the big thing is calculating the goal, risk levels, and safety metrics. Calculating all of these things, doing the simulations, doing classifying the faults, and supporting all the fault models that we just covered, both soft and hard. Finally, it needs to provide documentation for safety audits. And in all of these very important goals, again, the critical part would be the simulation. This would be the determinant whether I can do enough simulations, can I do exhaustive simulations to have good results or not. And it just so happens by pure chance that the company I'm the VP of has a ultra-fast fault simulator. It supports all the requirements I just mentioned, and it can run 200 million simulations in a week or so of real time on a single machine. We are very new, we are a young startup, we are penetrating the market now, and we're trying to tell people that safety is important, that simulation is important, that simulation speed is important, and that they should come talk to us. But even if you don't come talk to us, everything I said still applies. You need to start thinking about safety, you need to start learning the standards, and you need to start thinking, how are you going to prove that your design is safe enough to go into all the huge markets that are opening up in this decade, in the next decade, all requiring safety. So, the bottom line, workflow, you need to specify your hardware safety requirements, and for every design revision and every abstraction level, rethink about these things. Classify the faults in the safety-related hardware, compute the architectural metrics, optimize trade-off between fit, area, and power. Repeat. Every time you modify design, every time you go to a new abstraction level, lower typically, and this will help you get where you need. So what did we learn? What did we learn? What did I talk about today? Computers are fleeing their cages. This is a fact. You cannot avoid it. And that means that safety becomes center stage. This is the most important aspect. People will not buy unsafe cars even if they have wheezy CPUs inside. Unsafe, not buying. So we need to rethink again our design methodology, focusing on safety, reliability, availability, resilience, security. You can have other partitioning of this pie, but it's a multifaceted environment. Automotive industry has positioned itself as the leader in this because they've started earlier before many of the others, like drones or medicals and so on. And system engineering and the process to lower risks by identifying the hazard, assessing the risks, classifying them into buckets based on these parameters, specifying safety mechanisms that mitigate unacceptable risks and leave only acceptable risks, and then analyzing the design, assessing its residual safety level, and making sure by verification and testing that we are safe enough. And this actually is the reason all of this is in the context of HVC, because at the end of the day, this is another validation concept, another facet of validation that we need to address. So, any final questions? Yes, go ahead.
So out of curiosity, the redundancy part, when we have a 0 or 9, is it only for the cases of soft errors or are
No, it's for both soft and hard errors.
But the question, are there cases where the real-time result may be non-deterministic by design?
I'm not sure I understand. Now, why would I design anything to be non-deterministic by design? Why is that a good thing?
Because, well, that's why I'm asking. So the answer is obviously no, but there are cases, probably maybe in the aerospace industry, where you just need a fast answer and you, well, okay, so the answer is no.
The answer is no. I'm not talking about redundancy for speeding up things. I'm not talking about redundancy for modeling non-determinism. I have no idea how to design and validate non-determinism. I'm talking about purely about the question of safety for soft and for hard. And the best safety is through redundancy. Redundancy squares the probability of failure from, say, as I said, from 10 to the minus 5 to 10 to the minus 10. Therefore, it's the easiest and most expensive solution. Nothing can be more expensive because it's good enough, but many things can be less expensive and almost as good enough, which is the domain that we're talking about today. Any other questions? Yeah.
Do you use any statistical technique to compute precisely rare event probabilities?
So we don't use statistical probabilities to figure out where an event will happen, but we do compute the probability that an event will be critical, which is what I mentioned before. If I take, and typically these things are not general purpose, they're not running games, they're running a very specific hardware, they're running a very specific software sequence. If I simulate this software sequence from time 0 to time n, and each time I have a potential error on this flow, and 80% of the time points lead to no problem at all, and 20% cause a failure, then overall I can, equivalent situation is to say 20% of all the faults here will be critical, because the faults are completely random over time. So 20% of the time a fault will be critical, 80% it will not be critical. Based on, I measured all the possible time points, and 20% of the time points are critical. So we don't use statistics before the simulation, but we use exhaustive simulation, and then you take the results of that simulation and you figure out what the probability of a problem, of a fault becoming a problem. Any other questions? Yeah.
So, you spoke a lot of possible applications, but do you have real applications in some automotive companies?
So yes, we have an automotive product that we are offering to automotive companies. The automotive companies themselves are not our customers. They are our customers' customers. So we are talking to the tier 1 companies that create chips and sell them to the automotive companies. The automotive companies usually integrate a system built from components from other companies. So absolutely, we're talking to some very major companies who are making chips for automotive, And they're looking at this for two reasons. One, it can give them an advantage, and two, it can give them a disadvantage if the competitors will take it and they will not. So it bites you both ways. The first one will have an advantage, and the last one will be at a disadvantage. So we are talking to several big companies in this area to understand, they need to be convinced.
If you have any feedback from those companies, if they really got some benefit out of it.
So we have some initial examples that we played with, but right now I said we are a very young company, okay? So we only offered, put this in the market this year. So what we're telling these companies, and we're telling people who are interested here, is don't trust me, I'm talking. What they need to do is take this, take an example, run our tool on their example, study the results, and then they should be convinced. This is what we are now signing all the NDAs and so on to get these companies, these leading companies, to evaluate. And once they do evaluate and see how good it is, we're expecting to do sell. So, like I said, very, very young startup.
Good luck.
Thank you very much.
Other questions? Well, thank you very much.
Thank you.